discuss now is start discussing is information theory. It is not only because of information theory, but it's also because the quantities that arise in quantifying information are actually also the quantities like the entropy or the Kullback-Leibler divergence, which will play a major role in other subjects. Okay, so in some sense, information theory offers a universal language for describing a broad set of subjects that go from information theory, coding theory, statistical mechanics, statistics, statistical inference, etc. Okay. Okay. So the key question that we want to ask is how do we quantify information? Okay. In order to be more specific, let us consider a specific problem where there are two persons, Alice and Bob. So these are the usual characters in information theory. So so Alice does not know what is the value of a certain variable x, and so Bob knows what is this? What is the value of x? So Alice will ask questions to Bob, and as a result of this question, Alice will learn what is the value of x. Okay. So one operational way to define how much information is contained in the answer of Bob, which essentially also is equal to the is a measure of the uncertainty of Alice about x, is the following. So you can ask how many binary questions need Alice ask to Bob in order to find out what is the value of x. So by number of binary questions I mean yes or no. So questions which have a yes or no answer. And so that can have just two values, okay, yes or no, 0, 1, or whatever, okay. So now, for example, let us specialize to a particular case. Imagine that Alice and Bob knows that x will be in a set of four possible items. So x can be either A, B, C, or D. And then one way to ask questions is, say, Alice can first ask whether x is equal to A or B, or it is not equal to A or B, which is equal to C or D. And then, so this is the first question. And then, depending on the outcome of the first question, she may ask a second question. In this case, she would ask a question, is it A or is it B? And in this case, it will ask a question, is it C or is it D? Okay. So in this case, you would say that the value of so the information content of x is 2, because there are 2 binary questions to be asked in order to find out what is the value of x. Okay. Now, however, there is also another way in which Alice could ask questions. So she could ask, is it A or not A at the first step, first question Q prime. If it is if it is not A, then if it is A, then she would know what X is. If it is not A, then she can ask, is it B or is it C or D? And this would be a second question. And then she can ask if it is not B, then she can ask whether it is C or D. Okay? And this is a third question. So now you see that actually the number of questions that Alice needs to ask actually depends on what is the value of A. It can be either 1, 2, or 3. Okay, so indeed we need to be a little bit more precise here and realize that when x is actually a random variable, and then the number of questions that Alice needs to address is actually a function of x, so it is also a random variable. Okay? So then the best way to quantify the amount of information is to use the expected value of the number of questions. Okay? Okay, so now let us take 2 examples. So imagine that in case A, let's say case A, the probability of x is equal to 1/4 for all x. In case B, the probability of A is equal 1/2, the probability of B is equal 1/4, and the probability of C is equal to the probability of D is equal to 1/8. Okay, so then you will see that this expected value depends both on the way in which you ask questions and which is in this case Q or Q prime, and on what is the probability distribution. Okay, so if in case A, then if you ask question with Q prime, then the expected value of the number of questions you have to ask with this scheme, well, this is always equal to 2, okay? But if instead you use this other way of asking question, you will get n9/4 if you do the calculation. Well, because, well, with probability 1/4, you have to ask one question because it is A. With probability 1/4, you have to ask 2 questions. And with probability 1/2, which is C, the probability of C plus the probability of D, you have to ask 3 questions. Okay? So if you do this calculation, you get 9/4. However, this is if the probability is uniform, but if the probability is given by this one instead, then again the expected value of the number of questions you have to ask in this case is always equal to 2. And the expected value of the number of questions you have to ask according to these other way of asking questions is 7/4. Okay, so you see that if Alice wants to be parsimonious in the way in which she asks questions, then she will choose the way to ask questions that minimizes the expected the number of questions that she expects that she has to pose to Bob. Notice that, of course, if you want to quantify the information of X, then this measure of what is the information content of X is an a priori measure, is a measure that Alice wants to get before asking Bob. Because after she hears the answer of Bob, well, she would know what X is. So her state of uncertainty will be just dispelled, okay? So this is why we use the expected value here, okay? Notice also another property that these results do not depend in any way on what is what are we talking about, what are A, B, C, or D. It only depends on their probabilities, okay? So this expected value, so the amount of information is only a function of the probability distribution, independently of what X stands for. Okay. Okay. So the other thing is, say, if you look more closely at this result, then you see that you have to ask questions. So the answers which are most likely should be the one for which you have to ask fewer questions, okay? And the ones which are less likely are the ones for which you want to ask more questions. So indeed, say if you want to ask to your Italian friend who won the Italian championship last year, then most likely, I mean, your first question would be most likely, was it Juventus or not? Okay, so because typically Juventus is very likely to win Italian championships since the last 20 years. Okay, so very good. So if we put all these together, then one tentative way of defining the information content of a random variable is essentially equal to the minimum on all possible ways of asking questions of the expected value of the number of questions that you have to ask. Okay? So this this is this is a definition of the information content of the random variable X that essentially summarizes what we have said so far. And I'm using here this square bracket because x is a function, is a random variable, so it's a function from a sample space to the real, or to this set here in particular. And so h is a function of a function that is called functional. Okay? Okay, very good. Now, before going on, I want to discuss instead a different problem, which is the problem of coding. So the problem of coding is the following. So again, there are Elvis and Bob. But now the problem is that Bob is communicating the value of x to Alice, but this communication takes place on a binary channel. Okay, and the way it works is that they decide on a code. A code is a function that associates to each element of the values of x a string of bits. Okay, so this set here is the set of string of bits. So to each values of x, possible values of x, you have what is called a code word C of x, which is essentially a string of bits. Okay? And then if Alice and Bob have to define on one code, have to decide on one code, and if they want to be efficient, they may want to find the code such that they have to transmit the minimal number of bits. Okay, so what they want to minimize is the expected value of the length of the bit string that they have to send. Okay, well, L is the set, is the length of the code word that corresponds to x. Now, of course, there are many codes. Okay, so for example, in this case, where you have four items, you have a code C, which is say where say A corresponds to 0, 0, also say to 1, 1, B corresponds to 1, 0, C corresponds to 0, 1, and D corresponds to 1, so 0, 0. Okay, and also, but you can have any other association between values of x and bit strings. And a quite interesting thing is that essentially you can see that each way of asking question in this problem here corresponds to a code. Okay, so if you say that yes corresponds to 1 and 0 corresponds to no, then you see that A would correspond to yes to the first answer to the first question and yes to the second question. So it would have correspond to a bit string of 1, 1. This would correspond to a bit string of 1, 0. This to a bit string of 0, 1, and D to 0, 0. Okay, so likewise, this would correspond to a different code where A corresponds to 1, B corresponds to 0, 1, C corresponds to 0, 0, 1, and D corresponds to 0, 0, 0. Okay? So, and now you see that the most efficient way of asking, of coding your messages in order to minimize the number of bits that you have to, that you expect you have to send, is exactly equal to the problem of asking question in the most efficient way. So the fact that these two problems are exactly the same, so the fact of eliciting information and dispelling your state of uncertainty about a certain random variable x by posing binary question, and the problem of coding, the fact that they are the same, it's sort of non-trivial and interesting. Okay. Okay. So now let me discuss this problem more in general and give you the main result. And so of course you can verify that the solution to this problem is actually works, this definition works for these simple examples that we have discussed. But in the most general case, you have to be a little bit more general. In particular, what one can show is what is called the Shannon Theorem, which is the following. So now imagine that Alice and Bob exchange these messages very frequently, or let's say, or that Alice asks this question every day, and every day the answer of Bob is a random variable which is independent and identically distributed from the same distribution. So in other words, what we are interested is in sequences of answers, so that we call a message. A message which I just denote by X is a sequence of n simple answers, and that I will call generally characters. So a message is a form of characters, where these xi are IID from the same distribution, here xi equal to x, which is equal to px, where this x belongs to some finite set P. Okay? Okay, so then what Shannon Theorem tells us is that the number of bits that that are needed, or the number of binary questions that A has to pose to B, is almost surely so the minimal number of bits that are needed is almost surely equal to h of x which is equal minus sum over x in p of x log p of x, which is the expected value log base 2 of log base 2 of 1 over dx. Bits per characters. So, in other words, if Alice and Bob exchange these messages very, very often, and then asymptotically, when the length of these messages goes to infinity, the number of bits that they need for each character is at most equal to this object, and this object is called the entropy. Okay, so this is it's called entropy. Okay, so we have already seen this object when we were discussing the asymptotic equipartition property. I need say the main ideas of the proof of this statement is based on the asymptotic equipartition property. So let me remind the asymptotic equipartition property. So the asymptotic equipartition property tells you that if you have this set an of epsilon, which is the sum of all sequences or messages, such that 1 over n times the log, I'm taking log base 2 of the probability of the message, plus h of x, that is defined exactly like that, is less than epsilon. So if you define this is the set of epsilon typical sequences or messages, then we have that say the probability that you get a sequence from an is essentially equal to 1. So this is this means that if you draw at random one of these messages, the probability that this message belongs to an of epsilon is essentially equal to 1. The second thing is that the number, say because of this, the number of messages in the epsilon typical set is 2 to the n h of x. But here I'm using log base 2, so I have to put a 2 here. Okay. So then what does it mean? For our problem, what does it mean? Well, it means that Alice and Bob, if they want to exchange these messages, what they can do is to consider a code where C of x is between 1 and A of n of epsilon. If so Alice and Bob can attach an integer number C of x to each of the messages, a different integer number to each message, and this number can be between 1 and an of epsilon if x is in the epsilon typical set, and whereas C of x will be larger than the number of messages in the epsilon typical set if x does not belong to the epsilon typical set. So what does it mean? It means that essentially you you take all your messages, and in this epsilon typical set, and you just label them from 1 to an of epsilon. Okay? Then you have this label, which is an integer that goes from 1 to the number of messages. And you take the code as the binary representation of this integer. Okay? This is a string of bits, and this is your code. Okay? It's just the binary representation of this C of x. Then, essentially, this property tells you that almost surely you will only need to send messages which have a C of x which is less than this, and this property tells you that the number of bits that you will need is just h of x per character. Okay? So in the sense that 1 over n times the log base 2 of C of x, so this is the number of bits in the binary representation of C of x divided by n. So if you want, is the binary is the number of bits per character in message x, used to code message x. So because of this, if x is in the asymptotic, is in the epsilon typical set, then this will be less or equal than 1 over n times log base 2 of an of epsilon. And because of this, as n goes to infinity, this goes to h of x. So, and almost surely, so this, almost surely, n is above will exchange a message which is in the epsilon typical set, so that this will be, this inequality will be sure, will be true almost surely. Okay? So, this is the content of Shannon Theorem. There are other ways in which you can show that the entropy is the right measure for information. And one way to do this is it's based on the following observation. First, well, as we said, this the entropy is an expected value of something, of a function, but it only depends on the probability distribution. So it should be a function of the probability distribution of the random variable x. Okay? And the second property that you want is that, so this is essentially the sum over x of p of x times f of p of x. Okay, so now we want to ask, what should this function f of p of x be? Now the second requirement is that if Alice want to ask a question which is actually composed of two completely unrelated questions, so if x is actually equal to y and z, where y and z are independent, then we want that the entropy of x should be equal to the entropy of y plus the entropy of z. Why? Because essentially the number of any answer to a question that has to do with y does not give you any information on z, and vice versa. So there is no, so you can either ask about x, y, or ask about z, but any, so the amount of information, the number of questions that you have to ask in this case must be the sum of the number of questions that you have to ask for y and the number of questions you have to ask for z. Okay, so if you plug this, so this means that the p of x, which is equal to y and z, must be equal to the product of p of y times p of z. And if you take this definition, this tells you that the expected value of f of px or py, pz must be equal to the expected value of f of p of y plus f of p of z. Okay, so essentially your function f should satisfy this property that for any py, pz positive, the f of py, pz must be equal to the f of py plus f of pz. Okay. So, well, if so, the solution to this equation for f is essentially that f of x should be a times log of say log 2 of x. Okay. You can check that if you take this f, then this satisfies this equation. In order to prove it, then you can do it as an exercise. Okay. So now, third question is that well, we want that if we just want to know about a variable that can take two values, 0, 1, and with equal probability, then we want that the entropy is measured in bits, so we want that the entropy should be equal to 1. So we want essentially that f of 1/2 is equal to 1. Then this means that f of x must be equal to minus log 2 of x. Okay, or f of p should be minus log 2 of p. Okay. Okay, so this is an alternative derivation, and you can find other derivations as well. So, so one property of the entropy. So if x can take only values in a finite set, then the entropy of x must be positive and less than log 2 of chi. Okay, well, this limit corresponds to the situation where p of x is equal to 1 for some x which is equal to some particular x star, and is equal to 0 for x different than x star. So this probability distribution is probability distribution of a constant. So x is not a random variable, it's a constant which is equal to x star. And the entropy of a constant is equal to 0, which means that actually if something is a constant, then you don't need to ask about its value, in the sense that if Alice assigns this probability distribution to x, then she already knows what x is. She does not need to ask any question. On the other hand, these other limits correspond to the situation where Alice is as uncertain as possible about the value of x. And so the probability of x taking any value is equal, and by normalization one must be equal to 1 over k. And so notice that this distribution actually encodes maximal ignorance, because if you make any permutation of the possible values of x, then the probability distribution remains unchanged because it's just constant. So this tells you that this probability distribution does not distinguish in any way among the different values of x. So this means that it encodes a state of maximal ignorance. And so correspondingly the entropy is maximal when you have a probability distribution of this type. Okay. Okay, so then there are different ways in which the entropy can be generalized. So of course, if you have a random variable which is a vector of random variables, then you can define the joint entropy, which is just minus the expected value of log base 2 of the probability of the random variables x1, xn. I remind you that when I write capital X here, I mean these are random variables of which I'm taking the expected value. Okay. So this is the natural generalization. So we can also define a conditional entropy. In exactly the same way. We can say that if we have two random variables x and y, we can consider what is the entropy of x conditional on y. This is just defined as the expected value of log 2 of the conditional distribution where x and y are random variables. So what is the meaning of this object? So this is telling you how much would you learn on x if you if you knew y. Okay. So if x and y are dependent random variables, then knowing y changes your state of knowledge about x. And the conditional entropy tells you by how many bits would your state of knowledge change. Okay. And of course, because the conditional distribution is equal to the joint distribution divided by the distribution of y, you can substitute this. And this is minus the expected value of log base 2 of p of x, y, divided p of y. So you see right away that this gives you the entropy of x and y because of this, minus the entropy of y. And so and this is exactly what I was telling you before. So And this is quantifies your how uncertain you are about x and y if you don't know y. Once you know y, your state of uncertainty is decreased by the entropy of y. And this is precisely how much you learn about x if you know y. Okay? And very good. So of course, so this allows you to write the joint entropy as the entropy of x given y plus the entropy of y. But of course, this is symmetric between x and y, so you can also write it as the entropy of y given x plus the entropy of x. Okay? So, and you see also that, so if x and y are independent, then this just this is just a product of the two probability distribution. So P of y just cancels, and here you just have h of y. So this tells you that if x and y are independent, knowing y does not change at all your state of uncertainty about x. And also tells you that if x and y are independent, then as we said before, the entropy of x and y is equal to the entropy of x plus the entropy of y. So this, by the way, tells you that if you a state of maximal uncertainty about a certain set of random variable x1, xn is the one where these random variables are independent of each other. Okay, so this entropy here is always less or equal than the sum over I from 1 to n of h of xi, and this is a situation which is obtained when all the xi are independent. And so the state of maximal uncertainty is the one where all variables are independent. Okay. Okay, so there is another thing I want to discuss before, which is well, what we have discussed so far is how you quantify information for random variables that are discrete and in a finite set. Okay. Of course, say if your set is discrete but is infinite, then this this definition extend in a natural way. But what about the situation where the random variables are, you have a random variable x, which is real, okay? So how can you quantify how much information you gain if you know x? We can go back, so what you can think of is to write down an analog of the entropy, which is essentially, again, the expected value is minus the expected value of log base 2 of P of x. And now P of x is the PDF. So this is minus the integral minus infinity to infinity dx P of x log 2 P of x. Now, this as a measure of information, as an absolute measure of information, has problems. First, because you can show that h of x can be negative. For example, if you take x between 0 and 1, 8 uniform, and you compute this integral, then you will find that h of x is equal to minus 3. Okay, so what does a negative entropy mean? Okay. Second problem with this is that now if I make a change of variable where say f of x, for example, is a monotonously increasing function of x, then if x is a discrete variable, then this just corresponds to changing the labels of x, because it maps every point of x into another point of y, but the distribution is exactly the same. So you would have that h of x in this case would be equal to h of y, because the number of questions that you have to find out to see what is x is exactly equal to the number of questions that you have to find out, that you have to make to find out what y is. Okay, this is if x is a discrete variable. Okay, okay, discrete. Now, if it is continuous instead, well, we know that the distribution of y is actually equal to the distribution of x divided by the absolute value of the first derivative of x. Okay, so if you plug this into this formula, then you see that this formula will tell you that the entropy of y is equal to, well, you have the expected value of log 2 minus the expected value of log 2 of py, which is p of x divided by f prime of x. But this is so this part gives you h of x, but then you have an additional term which is the expected value of the log base 2 of f of x, f prime of x. Okay. Then so then you see that if you change variables, if you change a parameterization of your variable x, then if the variable are discrete, then it doesn't change. But if the variable are continuous, then it changes. Okay. So where does this problem come from? Okay. Now the problem is that essentially, if x is a real random variable, actually, if Alice wants to know the exact value of x, then she has to ask an infinite number of questions, because the binary representation of a real random variable is a sequence of an infinite number of bits. Okay, so the number of questions that you have to ask is just infinite. So then it's much more reasonable to ask the question, Imagine that Alice wants to know the value of x to a certain precision delta. Okay? Then we define a quantized variable x of delta in the following way. So imagine that this is the probability distribution P of x, the PDF, okay, which is something like this. And now we divide x in intervals of size delta. Okay, so this interval will go from I delta to I plus 1 delta. Okay, and then in each of these intervals we find the midpoint, this value xi. And the value of xi is defined by the midpoint theorem, such that the probability of xi is equal to 1 over delta times the integral on the interval of the probability distribution. Okay? So then we define a random variable x which takes value on this xi, and we say that the probability that x delta is equal to xi is equal to delta times p of xi, or which is equivalent is the integral is this probability here. Okay? So it is also clear that this way of defining the probability is normalized. If you sum over I, then you get 1. Okay, and I goes from minus infinity to infinity. Okay, very good. Now this is a discrete random variable. Okay, so the entropy of this discrete random variable is well defined, and it's actually minus the sum over I from minus infinity to infinity of this probability P times log base 2 of the same thing, delta times P of xi. Okay, now you see that I can take so this log 2 of delta times this is log 2 of delta plus log 2 of P. Log 2 of delta, I can take it out, so this there is a term minus log 2 of delta. And then there is a term that is minus the sum of I from minus infinity to infinity of delta P of xi times log base 2 of P of xi. Now you see this is very similar to the integral, because essentially delta is a dx, and xi is in the interval between is in the interval I. So this is if delta is very, very small, then this is well approximated by minus log 2 of delta minus the integral dx p of x log p of x from minus infinity to plus infinity. Okay, which is so the end result is that when delta is small, then if delta is very, very small, then this is h of x minus log, is also log 2 of delta. Okay? Okay, so then the meaning of this equation now is clear. So if you want to know a random variable x to a precision delta, then you have to ask minus log 2 of delta question plus an offset which essentially is given by this object here. And this object is called differential entropy. It's called differential entropy because it tells you what is the difference between this is the number of if you want, this is the number of bits in a real variable with up to precision delta. So if you take so if you want to know a random variable to n digits or to m digits, m binary digits, then you will have delta, which is equal to the minus m. And then this minus log 2 of delta will be exactly equal to m. So this tells you what is the offset that so if you want to know the random variable x for precision of say m bits, then essentially the number of binary questions that you have to ask is h of x plus m. Okay, so where delta is given by this. So say for example, if you go back to this example here, then you see that h of x in that case is equal to minus 3, because the first 3 bits in the binary representation of any x which is in this interval are equal to 0. Okay, because every real variable that is in this interval has a binary representation that after the comma starts with 0, 0, 0. So in that case, if you want to know a random variable of this type to a precision of m binary digits, then you have to ask m minus 3 binary questions. And also, well, the fact that this differential entropy is not invariant under reparameterization, as here, well, it is clear because you are changing the scale of, you are locally changing the scale. So this term here accounts for, so the precision, if you want, a precision of delta on this random variable y is not the same as the precision of delta on the random variable x. And if you want to relate the two, then you have to account for a change of scale that is given by this transformation here. Okay. So indeed, say if you have that y is equal to a times x, then you will have that h of y is equal to h of x plus log base 2 of a. Okay, and this a just account for the fact that when you make the transformation, a precision delta becomes a precision a times delta. Okay. Okay. Let's stop here.